Hi everyone, we have a new unit, unit number 6. I titled it Going Downhill Through the Carboxylic Acid Derivatives because when we interconvert from derivative to derivative, there are 4 derivatives, it is much easier to go downhill than it is to go uphill. And in fact, to get back uphill, we'll have to go through a ski lift through this carboxylic acid. I know the concept is a little bit abstract. I think you'll start to get it when we start drawing these molecules and categorizing them in their different classes. Okay, this is Unit 6. This is the first video. It's a little bit different than how I start the other units because I'm not going to teach nomenclature. I'm more concerned about introducing right away the reactivities of these derivatives and the general reaction pathways. And the first derivative is the acid chloride, and I'm going to draw them on top of each other. Okay, so we're going to start with what's called the acid chloride, and we've seen this already. In the last unit, we took a carboxylic acid and we converted it into the acid chloride. And I want to name it. Where do I put the name? I'll just put it underneath acid chloride. And it's almost exclusively the chloride. We don't really work a lot with acid bromides. Okay. The next derivative, and I'll explain why these are derivatives, but let me draw the 4 derivatives first. The next derivative is called an anhydride or an acid anhydride. Oh man. A-N-H-Y-D-R-I-D-E. Either acid anhydride or simply anhydride. It's oxygen flanked by both sides with a carbon-oxygen double bond. After that, we have an ester. And we've seen esters before because remember we did Fischer esterification in the carboxylic acid unit. So this is an ester. And then the last derivative is a amide. And let me give us a methylamide. Ah, good. I'm able to get it all onto the screen. A-M-I-D-E. Now, why do we call these derivatives? They are called derivatives, or why do we call them carboxylic acid derivatives? Because when we do a hydrolysis for each of these molecules, eventually water is going to attack the dot. And we're used to that. The nucleophile attacking the electrophilic carbon of the carbon-oxygen double bond. And we're going to kick out a leaving group. And here I'm going to put a dotted line across the bond that we break. Okay. When you hydrolyze any of these 4, it's not straight. When you hydrolyze any of these 4, you get the carboxylic acid. And for all of these, we have an ethyl group on the left side. So yeah, we are going to make, and where should I put this? Honestly, well, it doesn't really matter. I'll put it right here. Okay. Get the carboxylic acid. These molecules, or at least these classes of molecules, are on that cover slide. This was the ski lift. Because to be able to go back up stream or up the hill, you have to take the ski lift. And then from the ski lift, you know that you can get to the acid chloride. So this is a review reaction, SOCl2. Remember that? Okay. What about these others? How do we do hydrolysis? I'm not going to give the reagents. Right now, I'm showing you how everything is interrelated. Okay, so all the red ones are hydrolysis reactions, and you could even go this way from the acid chloride back to the carboxylic acid. Okay. All right. Next, Oh man, I had something else to say. Next. I said you could go downhill. So we should be able to give reagents, not in this video, but I'm showing you how, again, everything's interconnected. We should be able to have a reagent that goes from the acid chloride to the acid anhydride, from the acid chloride to the ester, and then from the acid chloride to the amide. And what else? Now we could go from the acid anhydride, go downhill to the ester. Okay, there's going to be a lot of arrows. This unit is large in terms of the number of reactions you have to learn, but I'm going to show you some general, just two. Well, I'll show you four, but two apply specifically to this unit. Two general reaction pathways that if you understand those two pathways very, very well, you can apply them to these arrows. Okay, where do we start? Stop. Acid anhydride to ester, acid anhydride to amide. Okay, and then what's the last reaction? Or last purple arrow? Ester to amide. Always going downhill. Now, again, if we have an amide and we need to get to the acid anhydride, there's no direct route up the hill. You have to take the ski lift. And you take the ski lift to the carboxylic acid, which takes you all the way up to the acid chloride, and then the acid chloride can go to the ester, or wherever you wanted to bring the amide to. Okay, going uphill. All right, I'm glad I got that. Oh, actually, there's one last derivative. There are four main derivatives. These four. But there is a derivative called the nitrile. And nitrile actually comes from the amide, but not this amide. If you have an amide that looks like this, what should we call this? I think people would call this a primary amide, and this is a secondary amide. And if you had another group, another methyl group, it would be tertiary amide. But anyway, look what happens if I do a dehydration. I'm not going to show you the reagent. We'll get to that when we talk about nitriles. But I am removing water, H, and an H, and an O. So there we have it. Two H's and an O. When I remove those, okay, I'm not showing the mechanism, so I'm just showing you that this is a really cool idea that we really did do a dehydration because we removed two hydrogens and an oxygen. We get what's called the nitrile. This is the fifth forgotten derivative, almost like I don't know the Beatles, the fifth Beatle. Everyone knows the four Beatles: John, Paul, um, George and Ringo. Who was the fifth Beatle? How about we do that? For my class, for 1 percentage point extra credit on the next exam, email me who the fifth Beatle is considered to be. There are several answers, but do that probably by, I don't know, the next 2 days. How about this? Email me before we meet again in class, telling me who the fifth Beatle is, because that's nitrile. But it's still a derivative. We could do a hydrolysis to go from nitrile to the carboxylic acid, and yeah, it matches 3 carbons, 3 carbons. Okay. I'm not going to explain. How much time do I have? Actually, I think I will explain. I want to explain the reactivities. Why are they in this order, this hierarchy? You can think of it 2 ways. You can think of it as how good, well, you don't even see that, reactivities. You can think of it as how good the leaving group is, right? Because look at all these dotted lines. I'm telling you that you're going to break that bond and you're going to kick out a leaving group. The better the leaving group, the more reactive. Based on your hierarchy, it's the acid chloride that's the most reactive. Awesome. You know what amides are? Your proteins, your enzymes, your antibodies, um, other proteins. Those are made of polyamides, so they're very stable. You're not going to start cutting up, your enzymes very easily. So that's great that amides are very stable. But why? How can we think of this? So the reactivities, you can think of it as either based on the leaving group. So more reactive if leaving group is stable. If you kick out a leaving group and the leaving group is a very stable molecule, then the reaction will go forward and your derivative will react. So that's one way to think about it. Or you can think of it as and, or if the partial positive on the carbon is very large, so more attractive to the nucleophile. So what can we say here? It's more reactive if it's more electrophilic, or if, oh man, I said that already. Second mistake. If carbon of the C double bond oxygen is very partial positive, right? What's another way to say that? Very electrophilic, more attractive to the nucleophile. Okay, let's take a look at each of these four: acid chloride, anhydride, ester, amide. Those four. Acid chloride, we already said, was the most reactive. It's at the top of the totem pole. And let us analyze the nucleophile. Not the nucleophile, the leaving group. The leaving group is going to be chloride. We're going to add a nucleophile, generic, okay? And we get this. What are we going to do? Nucleophile. Our leaving group is a Cl minus. Not bad, okay? Chlorine is electronegative, so it doesn't mind having that minus charge. Let's take a look at the next derivative, and we'll compare the two leaving groups. So the next derivative is called anhydride. I'll just use a shortened form. Not say acid anhydride, but just say anhydride. So here's your nucleophile. And take a look at what we did for the first reaction. The nucleophile attacked the dot, and the nucleophile now is attached to the dot. And we kicked out this leaving group here. Okay. The thing is, for an anhydride, you have two attack spots. The good news is that we drew a symmetrical anhydride, so it doesn't matter which dot you attack, either the dot on the left, or I'm not going to put a dot here, but the dot on the right. If you attack the carbon on the left, then your leaving group actually is this giant, not giant, but this larger molecule, the bigger piece. And what do we get? Okay, same result, but now my leaving group is this. It looks like a really good leaving group, actually, because this is a carboxylate. Carboxylates have resonance. So it's a bit of a conundrum. This negative charge is on a very electronegative atom. Also, it has resonance. But what trumps both of those things is that chlorine is electronegative, and it's also much larger. It's in a different period. As a reminder, do I even remember? C, N, O, F. And then under F is chlorine, then bromine, okay, and iodine. I'll just put that. So even though oxygen is more electronegative, chlorine can accommodate that charge better because it's spread out over a larger volume. So we're going to say that trumps the fact that this negative charge is on oxygen and you have resonance, but this is still more stable because it's larger volume. Okay. Now take a look at this, and let's compare it to the ester leaving group. The ester leaving group is this. How did I draw it? Like that. Plus Nu. And can you beat me? Can you draw the leaving group before I do? Here. Now the thing is, in the mechanism for some of these, the leaving group doesn't actually look like what I'm drawing. For the ester case, a lot of times that oxygen would be already protonated. Yeah, it would be protonated before it leaves. Okay. What I am telling you is that the fact that this is less stable than the leaving groups above it, that's why this is less reactive. Because theoretically, we can't really kick this out very easily. We have to go through some type of maybe catalysis, in particular acid catalysis, or base mediated processes. All of those words will become more familiar in the following videos. Now, this is pretty obvious. Choosing between these two, the one with resonance is more stable than the one without. So this molecule here has resonance. Okay, but this is a better leaving group than what? It's a better leaving group than what we get if we do a reaction with the amide. Okay, draw the products. Nu plus. So what is the anion here? What is the leaving group? It's an N minus. Yeah, N is electronegative, but it's not very electronegative compared to oxygen. So negative charge on oxygen is more stable. And so here we'll say that this O minus is better than N minus because more electronegative. How come that didn't win over chlorine? If you recall your acid-base chemistry, if you're comparing two atoms that have anions and they are on the same row, the same period, you go by electronegativity. But if you're comparing two atoms that are in different rows, you go by the size. You go by the size. Good. This is not very stable. And in fact, you know that this is a very good base. You've heard of NH2 minus. Well, it's very reactive going in the opposite direction because it doesn't want to stay as a negatively charged molecule. It wants to grab a proton and go back. Just like this doesn't really want to stay like this. It wants to, I don't know, possibly reattack and go back to the starting material. So all of that, in green, and we're showing the leaving group, all of that is considering how stable the leaving group is in terms of explaining the reactivity. What about the idea that the more reactive derivative has a larger partial positive, which makes it more electrophilic? Okay, well, let's see. We have definitely a partial positive charge here. Okay, so what is some benefit? With the chlorine, it's electronegative and it's pulling electron density away. It's probably still debatable. It was definitely debatable when I took organic, whether it's really due to the stability of the leaving group or whether it's really due to the attractiveness of the partial positive carbon. Okay, so we're going to rationalize this, that oxygen is pulling electron density away, same with the chlorine. So how come this doesn't do the same thing? There are two, again, maybe you might think this is a hand-wavy explanation, but these lone pairs can easily donate via resonance, thus reducing the charge on this carbon, or this oxygen is not as electronegative as chlorine because its electron density is being pulled towards this oxygen here. Yes. Not satisfying, especially the way I described it, but we have to find, or at least try to find a reason why this is more electrophilic than this one. Okay. How about this? Okay, this one is a little bit easier. Because we don't have resonance going to the right, okay? Your resonance is actually going always to the left. Then then it would follow that this partial positive is less positive because these electrons are doing resonance always to the left, whereas this one could go to the left or right, meaning that it's not reducing that plus charge as much. As you can tell, I like the stability of the leaving group explanation a lot better. And this one here, okay, nitrogen lone pair easily. This is actually very common resonance in an amide. You could also think of it as, if you think back to the acid-base unit, do you remember that ammonia is more basic than water? I always try to memorize that because that helps me remember some of these trends when I apply it to, in this case, reactivity. Right? Water, oh man, sorry. Let's do ammonia. Ammonia is more basic than water. Let me draw it here. That's because the lone pair, well, for it to be more basic, it means that lone pair is more grabby. It will grab a proton faster and more easily than the lone pairs, even though there are two of them on oxygen. Oxygen really doesn't want to be, for the most part, positive. For nitrogen, it's not that bad. Okay, knowing that lone pair is more facile, I guess, or more loose, this resonance happens a lot easier, making this carbon much less electropositive than the ester. It doesn't matter to me how you memorize or how you explain the reactivities, whether you do the leaving group stability or the partial charge on the carbon. It's up to you. I believe both explanations are in the textbook. Now, I do want to go through some general reaction pathways because we have experience with carbon-oxygen double bonds with the aldehydes and ketones. And if you recall the type of reactions we had there, we were adding still nucleophiles, oxygen nucleophiles, carbon nucleophiles. We did not do nitrogen nucleophiles, but we'll do that later. So what am I saying? I'm saying that if you have a aldehyde or ketone, you have nucleophiles that can attack. Okay? But what about our derivatives? Right? These are aldehydes and ketones. What about our carboxylic acid derivatives? Is there anything fundamentally different about those? Yeah, we just got done talking about leaving groups. So all of your derivatives have a leaving group. And we could still have an attack by a nucleophile. And technically, not technically, but we're going to learn mechanisms in future videos. But you've seen this before. You attack and you break the pi bond and put it onto oxygen. But ultimately, you're going to lose the leaving group. See, the aldehydes and ketones don't have any leaving groups, and that's what's fundamentally different between your carboxylic acid derivatives and what we've learned previously in the unit about aldehydes and ketones. So here's your nucleophile, and here's your leaving group. Okay. What do you get when you attack here? When you attack your aldehydes and ketones? Eventually you get the substitution, but there was no leaving group. So you're typically going to make an OH, okay, when you do an addition reaction. Is there anything else? Yep. So huge difference. Huge difference. Let me show you the two general pathways. If you are very reactive, and what are the reactive derivatives? The first two on top of the hill, chloride and anhydride. Those are very reactive. Chloride and anhydride. When you're very reactive, you don't need help. Don't need help. Don't need, in particular, acid catalysis. So your reaction, and we'll use acid chloride, you'll have a nucleophile, and you'll do the attack. I know I'm going a little bit fast. The good news is this is just general introduction to the different reaction pathways. For each reaction where I need you to know the mechanism, we'll go through that step by step using real nucleophiles, actual nucleophiles. But the way you kick out the leaving group is like that. So ultimately, yeah, you get back the carbonyl group. You get back the carbonyl group now with the nucleophile attached. That's if you're very reactive. If you're not so very reactive, which derivatives are those? The two bottom derivatives, ester and amide, then that's when you need some catalysis. So if you are an ester or an amide, you do need help. And that help comes typically in the form of acid. Let's take an ester. Sometimes it could come in the form of a base, but for the most part, we'll do acid. Okay. So here's your ester, and you're going to protonate it first. Okay, I'm going to use a generic H+. Normally, I don't like doing that. But it could be acidic water, it could be sulfuric acid, and we get the protonated. This is almost like a mechanism. We get the protonated ester. And that's when you do the attack. So now we bring in our nucleophile. Yep, I apologize for going so fast, but I think I could get through these first two general pathways. Well, we still make a tetrahedral intermediate. How does that look like? Yep, like that. See, this is tetrahedral. This is tetrahedral. Okay. But ultimately, we got to kick out the leaving group. Just keep in mind what the leaving group was. It was this one right here. Again, I'm not showing you the full mechanism, but I am showing you the final product. And it's similar to what we have here. It's just a different pathway. Sorry, you don't see that right there. Those are the two pathways. Let's remember that acid chlorides and anhydrides are very reactive. You don't need help. Do they attack right away? Esters and amides do need help, and typically that help comes in the form of acid that helps activate, makes it even more electrophilic to a nucleophile. Okay, the next couple of videos are going to be actual reactions, and we'll knock those out one by one, following these two types of mechanisms. All right. Sorry. Let me end off with this picture, actually. Okay, we're going to start filling in the arrows one by one.